You've probably heard the V12 died because of emissions rules. The EPA came in, governments cracked down, and that was it. The greatest sounding engine ever built was gone from your job site. That's the story people tell. It's not the real one. I spent a week going through engineering failure reports and Caterpillar's own overhaul data. And what I found is actually kind of embarrassing. For the V12, it didn't get regulated out of existence. It shook itself apart. And here's the part that'll really sting. A modern inline-six can outpull it at low RPM without breaking a sweat. There are 3 reasons the V12 disappeared. By the end of this, you'll understand all of them. And if you grew up loving the sound of old iron, fair warning, this one might hurt a little. Let's start with the murder weapon, the crankshaft. Engineering journals from 2018 tracked 25 years of V12 failures across heavy equipment and marine engines. They kept finding the same pattern over and over, something called three-dimensional coupled vibration. That sounds complicated, but the idea is simple. In an inline-six, the firing order is balanced. Each cylinder fires in a sequence that keeps the forces even. The crank just spins. Clean, smooth, predictable. In a V12, you've got 2 banks of 6 cylinders, arranged in a V shape, all hammering a single crankshaft from different angles at the same time. So the crank isn't just twisting from the combustion forces, it's also bending sideways and wobbling end to end. All 3 movements, all at once, thousands of times per minute. Here's a way to picture it. Take a metal rod, twist it, fine. Bend it, fine. Now twist and bend it at the same time, repeatedly, for 10,000 hours straight. At some point, something gives. What gives first in a V12 is the lubrication system. The vibration shakes debris loose inside the engine. That debris clogs the oil passages. Pressure drops. The bearings, which depend on a thin film of oil to keep spinning, start running dry. And when a V12 bearing spins dry, it doesn't just wear out quietly. It seizes the crankshaft. That snaps the connecting rods. And the connecting rods punch straight through the crankcase. It's not a repair at that point. It's a replacement. The CAT 3412 service manual actually draws a hard line on this. Once iron particle contamination in your oil passes 120 parts per million, you're not doing scheduled maintenance anymore. You are doing emergency damage control. The inline-six doesn't have this problem. The geometry protects it. The forces cancel each other. The crank just spins. Meanwhile, the V12 needed constant, almost obsessive maintenance just to keep from destroying itself. That's the first reason. Now let's talk about pulling power, because this is where the old school crowd always pushes back. Nothing lugs like a V12. You hear it all the time. The data tells a different story. Take the Detroit Diesel 12V92. Legendary engine. 18 liters. 700 horsepower. Sounds unbelievable at full chat. But look at where it makes its peak torque. 2100 RPM. That's high for a diesel. That's basically highway speed for a truck engine. That is not where you need torque when you're sitting in a pit, pushing material uphill, barely moving. Now look at a modern Cummins QSK19, an inline-six. It makes peak torque at 1,100 RPM, nearly at idle. You barely breathe on the throttle and it's already pulling hard. So why can't the V12 do that? Because of how it's built. To fit 12 cylinders inside one block, engineers had to shorten the stroke, the distance each piston travels up and down. Short stroke means less mechanical leverage on the crankshaft. Less leverage means less torque at low RPM. Think of it like a wrench. A long wrench gives you more turning force on a bolt. A short wrench gives you less. Same idea. The V12 piston has a short travel, so it can't apply as much twisting force to the crank at low speed. The V12 was built for output, for big numbers on a spec sheet. But a bulldozer doesn't need big numbers at high RPM. It needs low, sustained, grinding pull from the moment the engine starts working. And the inline-six does exactly that, every time, without drama. The V12 was a racehorse pulling a plow. Impressive to watch. Wrong tool for the field. That's the second reason. Now we get to emissions, but stay with me here, because it's not the angle you're expecting. When Tier 4 final regulations came in, and Stage 5 in Europe, every diesel engine suddenly needed a full exhaust aftertreatment system bolted to it. A diesel particulate filter, a selective catalytic reduction canister, A diesel oxidation catalyst. These are not small components. A DPF canister can be the size of a large propane tank. You need space to mount it, run it, and service it. An inline six is narrow. All 6 cylinders sit in a straight line. That leaves a usable gap on both sides of the engine inside the chassis. Plenty of room to mount the aftertreatment hardware. A V12 is wide. The cylinders spread out in a V. That's the whole point of the layout. By the time the block, the heads, and the ancillaries are in place, the engine fills the available width of the chassis almost completely. John Deere and Cummins both published engineering papers on this in 2016. Even after shrinking their aftertreatment systems by around 25% to save space, fitting the equipment alongside a V12 block was nearly impossible. In several configurations, the canister physically protruded outside the hood line. You couldn't close the panels. You couldn't seal the engine bay. So manufacturers weren't choosing the inline 6 over the V12 because the V12 failed an emissions test. The V12 couldn't even get to the test. It couldn't physically accommodate the equipment required to clean its own exhaust. That's the third reason. So let's put this together. The V12 was not killed by regulators. It was killed by a crankshaft that couldn't survive its own vibration. It was killed by a torque curve that peaked at the wrong RPM for real-world digging and pushing. And it was killed by geometry. It was simply too wide to carry the exhaust hardware modern regulations require. Does that make it a bad engine? No, it makes it a specialized one. You still find the Detroit 12 V92 in marine applications. You still find the Cat C27 in large mining haul trucks running wide, flat haul roads at consistent speed. Those are the right environments for it. Sustained high output, consistent load, flat terrain. But for excavating rock? Pushing dirt? Sitting at low idle all day in soft ground? The inline 6 won. It's simpler to maintain. It's narrower in the chassis. It makes its torque where you actually need it. And it can carry the emissions equipment without sticking out the side of the machine. Physics backed the 6-cylinder layout. And eventually, the industry followed. I know the 2-stroke Detroit fans are already in the comments. Fair enough. The 2-stroke V12, no valves, no camshafts, just a blower pushing air through the ports, is a completely different animal. And honestly, it's a more interesting argument. We'll cover that in the next video. For now, drop a comment. Keep the V12 or i6 forever. I want to see where people land on this. I'll see you in the next one.